Sofia Euro-BioImaging node from Bulgaria. And I want to share this tool, which is for a very specific stage of image analysis. It's really simple, free and open source. It's about segmentation. So when I think about segmentation, I usually think about this very specific and easy case of either whole cells or nuclei, which are fluorescently tagged, and we want to separate them like this, which is a very easy case. We can do it with a simple thresholding. But now let's suppose we have a harder case. For example, what about chromosomes, which I want to use as an example here. Let's say just histone H2B tagged with M cherry, and we want to segment each chromosome from the others like this. Now you can immediately see that this is a lot of work, and of course it's impossible to do it by hand. So in order to do this, we need to have some machine learning model, but even that will probably make mistakes. And actually, the idea of training a machine learning model involves lots of data, which, especially if it's a supervised network, in order to train such a model, first we need to make sure that we have sufficient amount of data. And to do that, we have to go through manual segmentation. So either as a pre-processing step or as a post-processing step of a specific machine learning model, sooner or later, we're going to have to go through manual segmentation. Now, most pieces of software have some form of manual segmentation implemented in them, but it's usually either in 2D or 2.5D, or in a way you have to go through each of the 3D slices and do the correction separately. So this is why this was our motivation to develop this very simple tool that I think you guys will like, because in specific cases, it's much easier, much more useful to do it like this. So now I'll just try to do a live demo. So this is just a cell with the chromosomes segmented. And what this tool is useful for is, first, if we're going to identify some mistake, and then we want to correct that mistake. But unlike the usual way this is done in most programs, here we can literally rotate the view in such a way that it's easier for us to actually draw out the correction that we want. So let's take these two objects now, and we can immediately see that there's a mistake here, that these red patches here are part of the blue chromosome. So what I can do is I can specify the colors of the labels that I'm interested in, and I can edit this 3D magic wand, and I can just draw out the structure that I want, and the program is going to take into account only the colors that I have specified. So regardless of the chromosomes that are behind me, so even if I'm at this angle, I can still draw out this red patch, and now I can recover it, and now it's correct. That's how it works, really simple. Now I can show you another case. For example, let's take these two. And we can also go forward in time. So let's imagine this is actually a movie, and we have a sequence of 3D images, and we can see that on the first frame, there's a mistake here, right? So this lower segment should be part of the blue chromosome. So I can do the same thing. I can specify which colors I'm interested in, and then use the magic wand to correct it. And now it's done. It's really simple. Now, another case that's very useful when we do segmentation processing is, let's suppose we have over-segmentation. So, for example, if we consider these two chromosomes and go forward in time, they kind of move together. So we can make the conclusion that they're actually part of the same label. So what I can do is I can merge them on all frames rather than doing separate corrections. And that's what it does. Now, if I go back in time or forward, we can see that they're now part of the same chromosome. Another useful thing that I can do is, especially in this case, when we have not a circular object like a cell, but something that's more like elongated, I can draw a center line. So here, let's say I'm interested in this chromosome, so I can place points like semi-automatically, and then the program is going to use these points to fit a spline curve in 3D, like that. And what's nice about it is that you can see that this curve actually goes through the center of the structure, which is not always the case in many of the existing software programs. Especially those of you who have done some skeletonization before, you know how difficult this problem is mathematically. In many cases, the endpoints of the structure are usually missed. So yeah, this is how we can do it in this too. We can measure this length and record it to a file and so on. And then finally, there are different types of views. So I can have this mesh-like representation, or the default one that we had before. And we can have black background and so on. And I can even change the colors of the labels if I don't like them for some reason, or do like a black and white view like that, and then highlight specific labels that I'm interested in. So okay, so now finally, let me go back to the presentation for a short time. So I just, obviously, I'm using this opportunity to popularize a paper that we recently published that we have used this software for. It's about chromosomes. So whoever is interested there, we explain exactly how we use this tool for manual and semi-automatic segmentation. If you guys don't care about chromosomes, that's also great. You can go to the GitHub link. It also has quite detailed instructions on how to use this tool. And you can always drop me a message and I can explain something else. Also, this is, like I said, this is open source. So it's open to any improvements or suggestions or integration into some of the existing platforms that we already have. So whoever is interested in that, you can just fork the repository, do some improvement, and then send it to me, and that will be great. I can update the link. So it's really up to us to use it and improve it in the way that we want. And yeah, thank you for the attention.